All right, Kendall, you had your hand up. You had a question on something here? Of course. So it says find the component form for the vectors indicated below. Round your answer to the nearest hundredth. So in number 11, we're told the magnitude of our vector is 4, and the direction for our vector is 218 degrees. So the formula that I'm using is that my component form for vector u is the magnitude of u times cosine of theta, and then the magnitude of u times sine theta. So that's the formula I'm going to use. So I'm going to have 4 times cosine of 218, comma 4 times sine of 218. And then I just go to my calculator and type this in. I do need to be a little bit careful here, because what mode should my calculator be in? Degrees, because the angle that we were given is in degrees. So be careful on that. I know mine is, because I just got done using it to do some degree mode stuff earlier. Oops. So cosine, or 4 times cosine of 218 is that, and then 4 times sine of 218 is that. So I have negative 315, comma negative 246. Ah, yeah, that would make a big difference. And if we think about the picture of this, this should make sense, right? So I have something that's 218 degrees, so 90, 180, and then like 30 more puts my vector down here in this quadrant. In that quadrant, both the x and y should be negative, which is what we're seeing. So that makes visual sense in terms of what the picture of this vector would look like. Matches what we're getting algebraically, which is good. David?
2, 4, 5, or 6.
Sure. Does anyone have a preference on 4, 5, or 6? Okay, I'll just pick one. I'll pick 4. I don't know why. So on 4, it says, given that A is the point 3,1, B is at the point 5, negative 4, C is at the point negative 2, 9, and D is at the point negative 1, 6. Find the component form and magnitude for the following vectors. And then 4 is, we're talking about the vector CA. Okay? So to get the component form for this, that's going to be x2 minus x1, comma y2 minus y1. That's the formula that I'm going to use to do that. So for C is my x1, y1. And A is my x2, y2. Got to be in that order, because that's the way the vector is pointing, where the beginning part of the vector is C, and the head part of the vector is A. So the initial part has to be C, and the terminal part has to be A. Anyway, so if I do that, x2 then is 3. x1 is negative 2. And then y2 is 1. And y1 is 9. So that's going to give me 5, negative 8. As my component form. Does that feel okay there?
Yeah.
Okay. And then if I want the magnitude of that, since I'm in component form, all I have to do is take the square root of those things squared. So the square root of 5 is 20, or the 5 squared is 25. Negative 8 squared is positive 64. And then 25 plus 64 is 89. And I don't think that that square root can simplify anymore. So that's where we're going to end. In fact, I think that might be prime.
So I found magnitude but not component.
So if you could have used the distance formula to calculate the magnitude that way also. I figured since I needed component form anyways, I would do that first because the magnitude calculation is a little bit easier that way.
Yeah.
But it's fine to do what you did and use the distance formula to calculate the magnitude. That's okay still. Yeah, good questions. Who else? Do we have others from this that we want to talk about? Okay, very good then. Let's move on then and start talking about the next set of topics. So we're going to continue talking about vectors. And what we're going to be focusing on today is vector operations. And we're going to start with just some definitions here, because we've defined this new kind of quantity to work with called a vector. It's natural now to want to talk about, like, what does 0 mean when we talk about vectors? How do we add vectors or subtract vectors or multiply, or what other operations can we cook up that involve this new quantity called a vector? And that's what we're going to spend today talking about. Just like when in algebra class, we talked about the complex numbers, then we spent some time talking about, okay, how do we add or subtract or multiply or divide or take the absolute value or whatever of these things, right? Same idea here. So we're going to start with a definition, and we're going to define what's called the 0 vector. So we denote the 0 vector as 0 with the vector symbol over top of it. And this has the component form of 0, 0, which means that it has a magnitude of 0. And no direction. So the 0 vector is the only vector that has no direction to it. And the reason we need to define the 0 vector as having no direction is that if we want to be able to do algebra with vectors, we want to be able to like add and subtract things from both sides of an equation, we need to have a 0 quantity so that we can have like inverses, so we can subtract things from both sides and have them cancel out. We need a 0 vector, something to represent that. So that's what's going on here. Okay. So that's relatively easy, very, I hope, intuitive. The next thing we're going to do is we're going to define vector addition. So let's say we have a vector u and another vector v. So to add two vectors together, we just add them component-wise. So we just add the x components together and the y components together, and that's it. This is a much more difficult process if our vector is given as a magnitude and direction. But it's easy to take a vector with magnitude and direction, turn it into component form, right? So more or less what we end up doing most of the time for convenience sake is if I have vectors described as magnitudes and directions, I convert them to component form, I do whatever addition and subtraction I might need to do, and then I'll convert them back from component form into a magnitude and direction. So, you know, it's like when you're doing your Spanish homework, maybe you convert it to English, you do the homework in English, and then retranslate it back into Spanish, right? You've probably all done little cheatsy things on foreign language assignments where you take something that's supposed to be done in the foreign language, you've taken to a more familiar context where it's easier to do the assignment, and then try to convert it back into the foreign language, right? Same idea here. So we're going to convert the vectors into this component form to do the algebra because it's really convenient. And then if we need to, we can convert it back into a magnitude and direction at the end. Worth noting that this vector of u plus v is sometimes called the resultant. That's kind of a more of a physicsy term, but the resultant vector is the vector that's the result of the addition of two vectors. So sometimes we might refer to that as the resultant vector. So this is the component form definition of adding two vectors. Let's talk about what it means if we've described our vector as a magnitude and direction, and show you guys why this component form makes life a little bit easier. So let's say that here's my vector u, and this guy will be my vector v. So what we do for this is we're going to take, oops, try to keep that direction looking somewhat the same. I'm going to take my vector u, and then I'm going to redraw like an imaginary xy axis, and now I'm going to draw vector v starting at where vector u ended. And now this vector from the origin to vector v is my resultant, u plus v. So I connected my vector from the origin to the end of this, and that's the resultant vector u plus v. So again, what we've did here, this is how we do vector addition if we have components, or component form. And this is how we do vector addition if we have the vectors as magnitude and directions. So potentially it looks like kind of a lot of geometry there going on in the magnitude and direction. Oops. Right? We'd like to avoid that because the geometry tends to take a lot of space. It's not super convenient to do by hand. Everybody okay with that idea? So that's what we mean by vector addition. We'll do some examples here in a few minutes. What I want to do now is start talking about vector multiplication. And there's actually 3 kinds of vector multiplication that we're going to talk about. So the first type is called scalar multiplication. or I guess we say the scalar product. So when I say scalar versus vector, these are two different kinds of quantities. So a scalar is just like a regular number, like 7 or 12 or square root of 10 or pi or 1/2. Just a number. There's no direction associated with a scalar. A vector has two components to it. It has a magnitude, a size that's just a number, and also a direction. So scalar multiplication is the multiplication of a scalar, so some real number, with a vector. I'm going to call that vector here u and define it component-wise as u1 comma u2. So k times the vector u, is a scalar product. That's what we mean. So it's a scalar times a vector. And this formula here is how we compute that, which is really easy, right? I just multiply the scalar to each component in my vector, and that's it. So let's do a couple of examples. So we're going to do 3 examples here. So we're defining vector u as the vector in component form -2, 4, and vector v as the component 7, 3. So the first problem we're going to do is u plus 2v. So what I'll do to start is rewrite this, where replacing my vectors with their component forms. Now, question, which operation should I do first? Should I do that scalar multiplication or the vector addition first? Should do the multiplication first, the same as what we did for the real numbers. I want to do here for the vectors. So 2 times 7 is 14, and 2 times 6, or 2 times 3 is 6. And now I can just add these two vectors. So -2 plus 14 is 12, and 4 plus 6 is 10. And that's that. Pretty easy, right? Nothing terribly complicated about this. Everything kind of works intuitively. So we'll do the same thing here. So 4 times the vector 7, 3. And here all we're doing is scalar multiplication. So I'll just do 4 times 7 and then 4 times 3. Everybody feel good on that one? Okay. And we have one more. So again, I'll start just by rewriting the problem and putting the component forms in place of the vectors. Then we said that the first thing we'd want to do is the scalar multiplication. We'd want to do that before we do the addition. Okay? So 5 times 7 is 35. 5 times 3 is 15. Negative 3 times negative 2 is positive 6. And negative 3 times 4 is negative 12. Then I just need to add these two vectors together. So 35 plus 6 is 41. And 15 plus negative 12 is 3. Everybody feel okay there? Okay. So now that we've defined vector addition and scalar multiplication, we can start defining what an additive inverse is. And as a result, we can define subtraction. So if we think back to like our elementary education, we know what an additive inverse is. So the additive inverse of a number is whatever you have to add to it to get back 0. So the additive inverse of 7 is negative 7, because 7 plus negative 7 gives us 0. If we want an additive inverse for a vector, it's going to be whatever we have to add to that vector to get back the 0 vector. Right? We can't add two vectors and get a scalar. We have to get it back a vector quantity. That's why we need that 0 vector. So, oops. What do you think what would be the additive inverse of this vector u that's defined in component form u1, u2? What would I have to add to this to get 0? Good, negative u1, comma, negative u2, right? Exactly right. So the notation we're going to give that is negative of vector u, which would just be negative u1, negative u2. Why did we need scalar multiplication to do this? Because this vector negative u is really defined as negative 1 times vector u, and that's how we're getting, that's where the scalar multiplication came into it. That's why we didn't define this before we defined the scalar multiplication. Is that okay? So now that we have the vector additive inverse, we can define what we mean by vector subtraction. Because if you think back again to your elementary school, what other way can we think about a subtraction problem? Like 5 minus 3, you could also think about as 5 plus negative 3, which is exactly what we're going to do here with vectors. Okay. So if we let u be the vector u1, u2, and v be the vector v1, v2, the difference of vectors u and v is defined as u minus v, which is equal to u plus a negative v, which is just u1 minus v1, u2 minus v2. So it's working exactly as we would hope. It works just like the addition did, right? Where we've just subtract component-wise. But we had to be a little bit careful about this because we needed this scalar multiplication before we could do this, and then we needed the vector inverses to be able to do this. So here's a nice or a little geometric way of kind of thinking about this. So just as an aside here, if I consider the vector u and the vector of negative u, what's the magnitude for each of these going to be? Well, let's say where u is just a b. So the magnitude of u is just going to be the square root of a squared plus b squared, right? The magnitude of negative u would be negative a squared plus negative b squared. But when I square a negative, what happens to it? Just positive. So they have the same magnitude. So what's the difference between a vector and its inverse or additive inverse? Has to be the direction. So these two have the same magnitude. So if this is vector u here, what's negative u going to look like? It's going to be the same length, but the opposite direction. Because if we add these two things head to tail, they basically just cancel out, right? Everybody okay with that idea? So just a little bit of a geometric interpretation of what we mean by this additive inverse. The next thing we need to do is define a special kind of vector. So a vector is called a unit vector if and only if its magnitude is 1. Why are unit vectors going to be of importance to us? Well, if we go back to first semester, we talked a lot about the unit circle, right? each point on that unit circle is defined as cosine theta times sine theta, right? What is the radius of this unit circle? 1. That's why we called it a unit circle. So what's going to happen then is these unit vectors are just going to be of the form cosine theta, comma sine theta. Okay. So how do I take a normal vector and transform it into a unit vector? So we're basically thinking about this vector u that has length of magnitude u, and we want to turn it into this unit vector. I'll say that's just maybe v, that has a length of 1. The direction is not changed, right? We're just shrinking it down so it has a length of 1. Well, I'm going to use scalar multiplication to do that. What would I have to multiply vector u by? Just 1 over its magnitude. So let's look at a quick little example here of doing this. Let's say that v is 5, negative 6, and I want to find the unit vector in the same direction as v. So I'm just going to call this unit vector u. So to calculate u, I'm going to do 1 over the magnitude of v times vector v. Well, to calculate the magnitude of v, I take the square root of each component, or the sum of the components squared. And then I'm going to multiply it by my vector v. So 5 squared is 25, 6 squared is 36. So when I add them together, I get 61. So I have then that u is 1 over the square root of 61 times 5, negative 6. If I then do the scalar multiplication, I end up with 5 over square root 61, comma, negative 6 over the square root of 61. Do I like the way that those components are written, though? What's wrong with them? Yeah, we have that square root in the denominator, right? We don't like to leave our final answers with square roots in the denominator. What do we do to get rid of the square root in the denominator? Yeah, we multiply the top and bottom of the fraction by that square root. So my final answer then would be this. Let's check our answer here real quick. Since this is a unit vector, if I compute this magnitude, it should give me 1, right? Everybody agree with that? So I'm going to use my calculator to do that because the square roots make things kind of yucky. So when I do something like this, I like to use the fraction command on my calculator, as it makes it easy to tell if I'm typing into my calculator exactly what I'm trying to. If you haven't ever used that fraction command before, there's a shortcut to get to it. If you press alpha and then y equals, it opens up the fractions menu. And the one we'd probably want to use in this class would be the first one, just the numerator over denominator version. And then you can just continue typing things in exactly as it looks, and you can use the little arrow keys to navigate whether you want to go into the numerator or denominator. Okay. And when we calculate that magnitude, we get 1. So I know that I've done this correctly because my vector that I've written has a magnitude of 1. Is everybody okay with that idea? That little fraction shortcut can be awfully useful.
Is that only if you're proving it's a unit vector?
That's just me checking my answer at the end to see that it is a unit vector. Yeah. So that's all I did there. Because I look at that and it's like, I don't know, could that be a unit vector? I don't think a no. Right? Did I do that right? Did I make a mistake? Can't really look at the numbers and go, oh yeah, of course that's going to have length 1 to it. I can't anyways. But it's an easy check on the calculator to make sure that you've done it correctly. Which is nice, right? It's always nice to have that reassurance. Okay. Do we feel good about taking a vector and converting it to a unit vector? It's not too bad, right? You're just basically dividing by its magnitude. The only problem is the magnitudes are often kind of yucky numbers, right? Next definition is called the standard unit vectors. Those are denoted with the letters I and J. So vector I is the vector 1, 0, and J is the vector 0, 1. Now this is important because we can use this or use these standard unit vectors to rewrite any vector as like a combination of these unit vectors. So what do I mean by that? So let's say I have the vector v that's defined as, say, CD. Well, I know I can rewrite the vector CD as, say, C0 plus 0D, right? No big deal there. I just broke it up into the sum of two vectors. Everybody agree with that? And I can pull off a C from the first vector and a D from the second vector. Since the other component is 0, I know if I scalar multiply the C or the D through, it only changes the one component. Everybody okay with that idea? And what you see there staring at you is our vector I and our vector J. So what this is basically doing the vector I is horizontal because it's 1, 0. So it's like going 1 unit over on the x-axis. And j is like the vertical because it's 0, 1. It's like going 1 unit up on the y-axis. So what we've basically broken this down into is you're going to go c units on the horizontal and d units on the vertical. So you just have like the vertical component and the horizontal component. So what purpose does doing this serve? Well, right, yeah, Kendall? Those are kind of standard convention that we use in really across mathematics. So did we pick I and j at random? Yes, but like everybody uses I and j for the unit vectors. So that's standard. But good question. Yeah, there's nothing magic about those letters, but that's just the letters that everybody uses. Just like when we write a variable, almost everybody uses x, right? It just, is there any reason we picked x? No, not really, but just what everybody used. So being able to break up a vector into component, in a combination of these unit vectors is not really important right now, but it will be a little bit later. So just kind of sit on that. I'm not positive with how far I'm going into this chapter, if it really comes back in a big way, but if we did the whole chapter, which I'm not going to do in the regular class, because we're not doing the 3D stuff and some of the more complicated 3D things. But if you're interested in engineering or whatever, you'll probably at one point take a linear algebra course and you'll do the heck out of this kind of stuff. I know there are a couple of us in here were interested in engineering at one point when I talked to them. Okay. So the next thing that we want to do is define another type of multiplication called a dot product. So let's say I have two vectors, u and v. We say the dot product of u and v is, so the notation that we use is just like a dot between them. Is u1 times v1 plus u2 times v2. Note that this result is a scalar, not another vector quantity. So the result of the dot product of two vectors is a scalar. We saw something similar to this in our algebra course when we talked about matrices. Remember that the determinant of a matrix is just a real number. It's not another matrix. So this is another operation kind of similar to that, where it kind of takes one type of quantity and converts it into another type of quantity. So let's look at some properties of dot products. So I'm going to use u, v, and w as vectors and c as my scalar. The first property is the commutative property. That just says that you can take the dot product in either order. U dot v is the same as v dot u. The second is the multiplicative identity that says the zero vector dot any vector is just going to be 0. There's a distributive property for the dot product. The next one is the scalar associative property that says if I have a scalar times the dot product of two vectors, I can multiply that scalar in at any point. So I could multiply it into the first vector and then take the dot product of the result. I could multiply it into the second vector and take the dot product of the result. Or I could take the dot product of the two vectors and then multiply the scalar in. It doesn't really matter when you multiply that scalar in, as long as you do it at some point, and you do it just one time. And the last one is the magnitude. And this says that u dot u is equal to the magnitude squared. What? What time does this class end? 10 more minutes. Let's prove a couple of these. We're not do all of them, but I'd like to kind of give you a feel for how you would go about doing this or why these things are true. Because at first glance, maybe some of these things aren't tremendously obvious. Okay. So I'm going to first start by defining my vectors u and v in component form. So I'm just going to call vector u, u1, u2, and vector v, v1, v2. And now what I'm going to do to prove this is I'm going to start with the left-hand side. and I'm going to try to do some algebra to end up with the right-hand side. Everybody okay with that plan? Because we are proving that they're equal to each other, right? So that's, yeah. We hope they're equal to each other. We need to demonstrate why that's true. So first thing I'll do is I'll just convert into this component form representation for my vectors. So I can say that that equality is true because it's just the definition of components, right? I've just substituted in the vector for its component form. No big deal. Now if I apply my dot product definition, I can say this, that the dot product is the first component, the product of the first components plus the product of the second component. Everybody okay there? Here's the tricky thing. U1 times V1, U1 and V1 are just real numbers, right? So they commute So I can switch the order of U1 and V1 because U1 and V1 are just real numbers. And that dot is now just multiplication between two real numbers. It's not a dot product between vectors. And now I'm going to use the definition of the dot product again, but in the reverse order. So I'm going to take this and convert it back to a dot product. And I know that V1, V2, and U1, U2 are just the vectors V and U respectively because of the definition of component form. And then I'm done. Yes, Kendall. So, oh, I just wrote that down wrong. That should be a 1 there. That makes a lot more sense probably, right? Okay. Yes. Excellent point. Thank you. Again, I make mistakes. If you think I wrote down something wrong or it doesn't make sense to you, please ask. You know, mistakes happen. I get it. No big deal. But I'm glad you're paying attention enough to go and thinking about what you're writing down enough to go, that didn't make any sense to me. Why is that going? What's going on there? And sometimes what I've written down might be correct still, and I need to explain it better than I did. And sometimes they just made a mistake and wrote down the wrong thing. In which case, I'm glad that somebody asked. Please, if you stop me, if things look weird. Okay. What if I want to do the multiplicative identity? How are we going to start here? Well, I'm just going to define the two vectors involved in component form and take a similar approach here. This one is much easier though, as there's much less to do. So what would I write next? Just rewrite my vectors in their component forms. Okay. Then what do you think I should do? Let's use the definition of the dot product, right? Because if I look at the right-hand side of the multiplicative identity, it's a scalar. And what's 0 times u1 going to be? 0. What's 0 times u2? What's 0 plus 0? And we're done. That's not bad, right? Seems very obvious now that you've seen it done why that would have to be true. Let's stop here. For tomorrow, what I'd like you to work on is numbers 15 to 22, and then also 25 and 28.